Let's try to solve more problems of solubility, because you will see that depending on the stoichiometry between ions, finding the solubility may be more or less challenging. Let's give a chance to this problem. So in here we are being asked to know the solubility of iron hydroxide. The iron hydroxide has a KSP of 10 to the negative 15, so this already tells you this is very small. The smaller the KSP, the less soluble your solid is. The question is, what is the solubility? Solubility again is how many moles of solid will dissolve in 1 liter, and it can be calculated as such, right? So notice in this case that there is a 2 in here, so for each mole of the solid that disappears into solution, there will be 1 mole of iron and 2 moles of the hydroxide. Therefore, how can we calculate the solubility? Well, first of all, notice that in our previous video, X was equal to the concentration of both ions. In here, X that we will find now will only be equal to the concentration of the iron. To find the concentration of hydroxide, we will need to multiply X by 2. So let's find the solubility of iron hydroxide. If this is by definition the KSP, it means that the KSP is concentration of iron. How much is concentration of iron? It's X. Does it have any exponent? No, because there's just 1 in here. Times concentration of hydroxide to the square. How much is the concentration of hydroxide? Is 2x to the square. Okay, so notice that I'm adding both 2 in here. Okay, 2x to the square. This is x times 4x squared, or if you will, 4x cubed. Alright, so this means that x is equal to the root square of KSP divided by 4. How much is x? So it should be 3 KSP, the KSP 7.9 times 10 to the negative 15 divided by 4, and that gives you a number. If you will, I can even do it. I'm just calculating it right now, and that should be elevated to 1/3. Okay, what I get is 6.5 times 10 to the negative 16 molar. Okay, hopefully that is correct. It's definitely very, very small, as you can see. Something tells me that this is not correct. I'll repeat the calculation some other time, and I may correct it later. Anyhow, now an extreme case, for example, is to calculate the solubility, that is, finding how many moles of solid will dissolve in 1 liter of calcium phosphate. Calcium phosphate in this case has a 3 and a 2 here. Okay, and you're given the KSP. Okay, so let's see if we can find the solubility. KSP is equal to concentration of calcium to the cube, concentration of phosphate square. So concentration of calcium is 3. Why is 3x? Because for each mole of solid that disappears, there is 3 moles of calcium appear, and this will be cubed, times concentration of phosphate, that is 2x, and this will be squared. Okay, so 3 cube x cubed times 2 square x squared, that is 27 times 4 times x to the 5th. Okay, so this means that x is equal to the 5th root of KSP divided by 27.4. Okay. Notice that this is going to be very, very small. All right, so which already tells you by the amount of KSP. These are solids with very limited solubility. Actually, calcium phosphate is used. It exists in your bones, and you may want to have bones that do not dissolve in water. So yes, calcium phosphate has very limited solubility. In this case, X is not equal to any of the concentrations of the ions in solution. To find the the concentration of ions in solution, you need to multiply by 3 or by 2. Okay? So careful with thinking that X gives a concentration of ions in solution. You can find the concentration of ions in solution, but sometimes, like in this one, it is not equal to any of the concentrations. All right? There's also a typical misconception that just by looking at the KSP, one can find out which one is more soluble. And that's only true if both compounds that you're comparing have the same cation and anion ratio. For example, in this case, it's asking you what is more soluble, barium chromate or silver chromate? Well, let's see. Silver chromate is here, barium chromate is up here. If you look at this, you would think, oh, well, silver chromate has a lower KSP, less displaced to the right. It should be the least soluble. But if you calculate the solubility using X, the same method that we used in our previous slides, you will see that actually the solubility is larger in silver chromate than in barium chromate. And that's because these two compounds, you get to calculate the X using different formulas. Therefore, the X or the solubilities cannot be deduced just by looking at the KSPs. It's something that the KSP is only indicative of more or less soluble as long as the two compounds that you're comparing have the same cation and anion ratio. This is not the case for barium chromate and silver chromate. All right?